Next up, we have Olivier Gauthé with Non-abelian symmetries in the ITensor soccer library. Please welcome Olivier.
Thank you. Thank you. Thanks for having me today. So, as mentioned, I will discuss about non-abelian symmetries in tensor networks and its implementation in the ITensor software library, which is a Julia library for tensor networks. So, we give a brief introduction to tensor networks, then some advertisement for the library that we developed at the Flatiron Institute in New York City. And then there will be a quite technical part about non-abelian implementation itself. And I will have a live demo if everything went well about how we actually use this in ITensor. So first, what is a tensor? It's a generalization of linear algebra to a larger number of axes. So when you have a vector, it's just an object, an array with one axis. When you have a matrix, it's an object with two axes, and you can generalize it to higher dimensions. And from a mathematical perspective, it's a multilinear form, and once you specify a basis, you end up with a multidimensional array that you can store on your computer. So in tensor networks, we end up with many different axes. So we need a diagrammatic notation to represent all of this. So this is called the Penrose notation, where a tensor becomes a box. And all the indices of the tensor become just, the legs of the tensor become just edges. And I can generalize the matrix product when I'm summing over the indices as the tensor contraction where I merge legs. So these are two vectors x and y because I have one leg that I index with I, and when I share the leg, it means I'm summing over it. And now the output has no index left. So that's a scalar, which I can see clearly because there is no leg in my diagram. And I can write quite complex expressions like this. And I can easily see that the output is a matrix because it has two axes. Tensor network is a quite recent subject, but with many applications. It originally comes from quantum physics, so I will focus here in its use in quantum physics. I consider an object, for me, it's a quantum wave function, and I represent it as a high-dimensional tensor. And this is way too big to store on my computer. Here I have 4 legs. Imagine that if I have a system of 20 particles, this will be 20 legs. And for 100 particles, that would be 100 legs. And it would scale as 2 to the power 100 coefficients. I cannot store it on my computer. So the point is, I will decompose this very large tensor into a bunch of much smaller tensors. And in doing this, I need to introduce these so-called virtual dimensions. And this is an approximation when the virtual dimension is small, but I can control the accuracy of my ansatz by setting the virtual dimension as big as I can. And for the physicists, this goes beyond mean field because when I select the bond dimension with 1, the state I obtain is a product of scalars, so that's what you get in mean field. But I can get beyond this because I can carry entanglement in my system. So as I said, it's a low-rank approximation of high-dimensional data with many applications. In quantum physics, this is extremely efficient because we know there is a link between the approximation I'm making, the accuracy of my ansatz, and which kind of quantum state I can represent. I have a faithful representation of any low-entangled state with a direct relation between the entanglement entropy of the quantum state I'm describing and the bond dimension in my system. And I can use many different ansatz. The most common one is so-called matrix product state, a so-called tensor trained by mathematician, but there's also so-called PEPs or three-tensor networks, and even one more exotic. So as you can see here, there are many legs, so you need a convenient way to deal with all these legs. And this is where ITensors comes in. So ITensor is a Julia library that is developed at the Flatiron Institute, and it allows to quickly build algorithm for tensor networks with large number of legs without digging too much into the details of how you define each of these objects. And it comes out of the box with many convenient algorithms so that you don't need to reinvent the wheel every time you want to write the tensor network algorithm. It's aiming for simplicity and high-level interface, such that it's accessible to non-experts in tensor networks. So how does it work? It relies on the concept of intelligent indices. Instead of constructing a tensor first, I first define the indices. Here, you see, I have this tensor network that I want to contract, and I have 4 tensors inside it and 5 edges that are labeled by Greek letters. So first, I define the edges as ITensor indices. Each of them has a hidden unique identifier, which is hidden. Well, I can see it, but the point is I need now just to remember I have these edges. I construct the tensors from the indices I just defined. So the size of this tensor is the size of alpha, beta, and kappa, which is defined here. Here it's always 2, but of course it can be anything. And now if I want to write the contraction, I can just say X is a product of these tensors. And now ITensor will detect these tensors share indices, because I know these indices like alpha is shared between A and B. Therefore, I will contract A and B over their share index alpha. Then I will contract with C. ITensor will detect that beta is shared with the product of A and B. So it will contract this temporary object with C, and then the same with D. And I don't need to specify anything more because everything is stored inside the tensor and the intelligent indices, and there is an automatized way to detect which indices are shared. ITensor is now a quite vast ecosystem with many different libraries. So the flagship is ITensors.jl. It's just aiming to be the most generic possible. So just generic tensor network libraries with just tensor objects and indices objects and little else. Except that, yeah, you also have GPU support and you're able to support many different backends. We have our own backends that are either Julia arrays. It can also be GPU or more fancy objects. But the objective is you should be able to use any kind of tensor and wrap it inside the ITensor.jl. If you're a physicist, you may be interested into specific applications like DMRG or TBD. These are into the ITensor MPS library, which is just a matrix product state library using ITensor. A very fancy one is ITensor networks, which is a very interesting library that can define tensor network and approximatively contract them on arbitrary graph. I think that's very fancy and quite useful. Finally, what I will focus on in this talk is the Fusion Tensors library, where we have implementation of non-abelian symmetries I will now explain. And just to say, this is a work in progress, so some of this, like ITensor MPS, you can use it right now out of the box. The non-abelian symmetries, you may need to wait a little bit more in order to before being able to use it on your own. So, what I mean by non-abelian symmetries is associated with group theory, so it's a very broad subject. The point is, you have a vector space, whatever this is, and you know that you have a group that acts on it. So here you have an object that can be a 2-element vector, but can be anything. And you have the concept of here a rotation, but it's an element of the group. And you know that under the effect of this element of the group, your object will transform in a well-defined way. You can define this even for wave function. Like if you have a 1D system, you can define the action of the translation on this system by just shifting every side by 1 unit. And this will be acting with a translation, that is an element of the group of translation, on your quantum wave function. This defines a so-called representation, meaning your Hilbert space of your wave function becomes a representation of the group. That's the mathematical name of this. And you can say that now, because of the group theory, your object will decompose as a sum of what we call irreducible representation. So it seems a bit abstract. Let's consider a matrix, a 3x3 matrix acting on a three-dimensional vector. I can decompose this matrix as its trace, plus the cross product of one vector that is defined univocally by the matrix plus this object that is a traceless symmetric matrix. So this is just one decomposition as trace plus antisymmetric part plus symmetric part. The point is, under the effect of the 3D rotation group, SO3, all these objects behave in different ways. This object is a trace, it's invariant under the effect of a rotation. This object is a vector, so it behaves as a vector under the effect of a rotation. And this is what we call a spin-2 or tensor representation. All of these are different irreps, and my point here is my matrix that was a 9-dimensional object can be decomposed as a sum of 3-dimensional objects that are completely independent from the perspective of group theory. And these irreps have fusion rules, meaning if I take 2 spin 1/2, I can decompose the tensor product of the space made of the tensor product of 2 spin 1/2. I can show that it decomposes as 1 spin 0 and 1 spin 1. And you can check that the dimension match. Here you have 2 spins of dimension dimension 2, because these are spin 1/2. So the dimension of this product space is 2 to the square, that is 4. And the dimension of the right is dimension of the spin 0, that is 1, and dimension of spin 1, that is 3. So I have 4 equal 4 in terms of dimensions. In this talk, I will mostly focus on the group SU2, which is the most common group you will see in quantum mechanics. But it's the rest of the talk is generic to any compact Lie group. And I will use the fact that for SU2, I know the irreducible representations are what we call spins in quantum mechanics. And I will, instead of labeling them with half integer as is the common way, I will label them by their dimension. So for me, 1 in bold letter, that's the dimension of the spin 0, and I will use it to represent the spin 0, knowing that it's both an irreducible representation and a vector space of dimension 1. Spin 1/2 is dimension 2, and spin S is dimension 2s plus 1. The first example I can mention is the S.S operator for 2 spin 1/2. So it's a 4-dimensional tensor. It has 16, meaning it has 4 legs, and it has 16 coefficients. However, I know this object lives in a can be decomposed as a sum of irreducible representation because I know that each of its legs correspond to a spin 1/2 representation. And I know I can rewrite this object as just the sum of 2 projectors, the projector of the singlet space and the projector of the triplet space. I have only 2 coefficients. More generally, for any quantum operator that acts on 2 spin 1/2 and outputs 2 spin 1/2, I can rewrite it as a function of only 2 parameters that here in this case I label as the eigenvalues of my operator. I want to only keep track of these 2 parameters in my whole tensor network computation instead of the 16 one. I can compress very efficiently my objects with only 2 parameters because thanks to group theory, I know that I can always recover all of these 16 coefficients from the 2 I'm storing. So this is here an 8-time gain in terms of memory. It can go to up to thousands. Typically, you store only 1 coefficient out of 1,000 if you were not to use a symmetry. So that's a huge gain in terms of memory. The mathematical framework is in order to implement non-abelian symmetries, I need to attach a group representation to any leg in my tensor network, which I was doing here by attaching a spin 1/2 to every leg. Now, I fuse the legs and I say my tensor as a whole lives on the space that is a tensor product of all the representation of all of its legs. And the tensor is invariant, meaning I only allow singlets in the complete product. Therefore, if I have 4 spin 1/2, I can compute the tensor product of 4 spin 1/2 and decompose it as a sum of irreps. And SU2 fusion rules tell me I can make only 2 singlets, 2 spin 0, out of this. And I will only keep these 2 objects. These were the 2 coefficients I was keeping previously. This corresponds to the number of singlets I can make out of the legs. To handle this, I will need so-called Clebsch-Gordon tensor and fusion trees. So a Clebsch-Gordon tensor, we know Clebsch-Gordon coefficients are the way to fuse two irreps on one product irrep. So if I take two spin 1/2, I know I can make a spin 1 out of them. And there are rules that tell me that, for instance, the up coefficient, if I take the state up for the two spin 1/2, I obtain the state 1 for the spin 1. And if I want the state 0 of the spin 1, I need to take the state up, down, plus down, up over square root of 2. And all of this defines a tensor because I'm just constructing a dense tensor and filling it with Clebsch-Gordon coefficients. And now this is a tensor. I can compute a tensor network out of this and define a so-called fusion tree, which will fuse all of my irreps into one single irrep. And I can just construct this explicitly as a tensor network of Clebsch-Gordon coefficients. And it defines the basis for my tensor. I can use this fusion tensor to project the tensor I had on the singlet space. So I can define a projector on the singlet space as the sum of all fusion trees that will give me a singlet at the top. And this will define a singlet vector, which I obtain by applying my projector on the singlet space on my dense array. And I can go back and forth the dense form of my array and the symmetric form where I only store a two-dimensional singlet vector. There is a difficulty here because there are different topologies possible for the fusion trees. So if I permute the leg of my tensor, I will implicitly also change the topology of my fusion trees. And this corresponds to a change in the basis of my coefficients. Therefore, when I change the topology, I have two different vectors and the coefficients here and there are not the same. So I need to change basis. The way to do it is I know how to deal with the dense array. I know how to permute the legs of a dense array. So I can start with my symmetric state with only two coefficients, project it back to its dense form that is now has 16 coefficients, permute it, because I know how to permute a dense array, then apply a new projector made out of the new fusion trees. And I will get a new vector that still has two coefficients. But I can do better. This object is just what I obtained by intersecting everything but the coefficient of my old vector. And this is defined only by the group. This is independent of the coefficient I'm storing in my tensor. This object is a 2x2 unitary matrix that is only defined by the Clebsch-Gordon coefficient and the theory of the group. It has nothing to do with what is the data I'm holding in my old vector. So I can compute this unitary once for all, then it's set forever because it's a pure mathematical constant. And I can reuse it over and over to compute the unitary and apply this unitary on my vector. I would just say that I need to conserve linear map properties. So I need to compute, let's say, singular values decomposition. So I will always conserve a form where I have two fusion trees, one for the domain and one for the codomain, meaning I'm matricizing my tensor. And it's here the block diagonal matrix that allows me to make efficiently tensor contraction as block matrix product. There is an optimization with 6G coefficients for the expert. I think I won't deal into this. I will now give you a clue about how we're implementing all of this in ITensor. So we are basing ourselves on the block arrays interface that define a nice block object that is here. It allows to define blocked arrays. Any dimension, I will focus on block matrices that I can access with this object block. So it's a very nice interface for block matrices. It's very generic. We used it inside ITensor to define a block sparse array object that store dense blocks, but the blocks may be missing because it's a sparse array. So either a block is present and then it's stored as typically a dense array, although it should be generic, agnostic with respect to the type of the block. Or there is the block is missing and then you just don't store it at all. You just need to be careful when you take views of a block that may be missing, so you may need to initialize it first. We also need the concept of symmetries, so we need to store group representation, and to store the space made of several irreducible representations. So we have so-called abstract sectors that encodes irreducible representations, and so-called graded unit range, that's an abstract unit range that contains symmetry sectors. As this is spin zero, this is a space made of one spin zero and two spin one half. I can define the tensor product of two spaces by computing directly with the nice Julia Unicode the tensor product of two axes, and this decomposes as a sum of irreducible representation as detailed by the fusion rule of SU2. And the nice thing about this interface is in quantum physics, we typically have several symmetries. If you know about the Hubbard model, you have one symmetry that consists in the number of particles. That's a conserved U1 quantum number. And one quantum number that's associated with the spin of your particle. And you can very easily define this object that is a Cartesian product of two symmetry sectors. It has both a number of particles and a spin. And I can define the tensor product of these objects in the same way as I was doing it before. Now, in Fusion Tensor, I will reuse a lot of the block sparse array. So I will store the axes of my tensor, including a bipartition that was corresponding to my domain and my codomain I mentioned before. A data matrix that just a block matrix I mentioned before. And a mapping to deal with all my fusion tree technology. And the point is, you should be able to use this object without knowing much about the internal structure, but as if it were any tensor, except that now you need to have a bipartition of the axis. So let me show you how it works. So here, let's say I'm defining S.S operator for spin 1/2. So this is a 4x4 matrix. I can reshape it as a tensor with no 4-dimensional tensor with dimension 2 on every leg. I define the domain legs as a graded unit range with a spin 1/2 everywhere. I need to define also the domain and the codomain. There is a dual due to some arrow convention. I will gladly explain it in questions. And now I can compute a fusion tensor by converting my dense array into the symmetric format. And if I look at what I have now, I have a 4-dimensional tensor with 4 axes. And the information I'm storing are only the 2 coefficients I was mentioning before. So I had a 16 coefficient array initially in the asymmetric format. And now that I converted it to the symmetric form, I only store 2 coefficients. But if I compute the norm, and if I compute the norm of my dense array, I see that this is the same. So I'm conserving the norm. I have as much coefficient as before, even though I strongly reduce the amount of storage I had to carry. And I can also check that I have the same information as before. If I take my fusion tensor and convert it to an array, I check that I have the same array as I had before all this conversion. So there's no loss of information when going to 2 coefficients. And the last thing I would like to show you is I can permute my array. So now I need to permute my array and still specify a bipartition of the axis. I obtain another array. I can check that the norm of this array is the same as before. But if I check the data matrix, so the coefficient I'm storing, they are now completely different. Because I've changed the basis, I needed to change the coefficient I was storing. But there is still the same amount of information here, just the coefficient are expressed in a different basis because the basis I'm using depends on the bipartition of the axis. As a last comment, due to the symmetries and the fact I have way less coefficient as before, the contraction now become extremely fast. However, the bottleneck of the computation now is a permutation of the axes. So it means when you're writing a complicated tensor network algorithm, you now need to be careful about how you're designing the permutation within the tensor network, because this is now the bottleneck of your computation instead of the traditional tensor contraction matrix multiplication. And that's, as of now, that's not simple, and we're doing it by hand, which is a bit cumbersome, but it's still worth it in terms of performances. So to conclude, ITensor.jl is a very versatile tensor network library that aims to be fully generic, agnostic to any application you will want to use it for, even though it's originally coming from quantum physics. And the new feature we're developing right now is non-abelian symmetries, which offers tremendous gain in terms of both CPU and memory. And this will be available when it will be available. And I would like to thank Luca DeVos, who's around this week, Carl Spies, Matt Fishman, and my student Maya. And I thank you for your attention.
Questions?
Hello, Olivier. Thank you for your talk. I think you may already know what my question will be, but I heard down the grapevine that there's a package called TensorKit that already supports non-abelian symmetries. So what exactly do you think your implementation will reveal that maybe TensorKit doesn't do well, or what do you think you'll achieve new compared to what's already implemented?
High-level interface. Like, TensorKit is very powerful, but when you're a complete beginner and trying to read the documentation, as you may know, that comes with a few difficulties. The point is, in ITensor, you should be able to run DMRG without knowing anything about tensor network, basically. And you should be able just to say, I want to implement SU2, so just say implement SU2 equal true, and everything will fall down the box. And the point is to have a consistent ecosystem. Now, for the technical parts, we will probably have some interface with TensorKit, because the way we compute the unitary only depends on your choice of Clebsch-Gordon. So we may call TensorKit as a backend in order to compute the unitary. But the objective is to have a very polished interface that's usable for people who are not expert on this. And all the technologies about fusion trees is designed to be hidden, such that basically only me knows about how it works. And you don't need to know anything about that to use it.
All right, thank you.
Other questions?
Well, since you mentioned that you are about to heavily refactor tensors, just wonder if you're going to put extra attention on using the new dash stream option for Julia. That
The new, sorry?
there's a new way to compile Julia. We use the stream option, which can automatically generate. Well, it helps to generate the binary libraries or executables.
Mhm.
And I'm asking this because we tried to use ITensors, but it's not compatible with Trem, and then we have to use other libraries. So I was wondering if you're going to put attention on that.
Okay, I don't know. I will be happy to discuss further.
Sure.
I don't know.
Okay, fair enough. Thank you.
Might have time for one more.
Any more?
Okay, yeah. We can thank the speaker again.